And I may even turn on the projector today. I'm feeling magnanimous. Okay. Well, it takes a while to hiccup. Is it doing anything yet? Try it again. Anything? Oh, there we go. Okay. Announced this last time, and I bet you all of you were here to hear it, but just to make sure. There he is. All right. The good news, bad news situation coming up again. The good news is next week is Thanksgiving week. Okay? And here's Demetri. Okay? And as such, of course, Thursday and Friday are state holidays. The school is closed Thursday and Friday. The bad news, though, is y'all don't have any classes next week. Okay? Get over it. Okay? Because we have professional meetings all week. I mean, Monday, Tuesday, and Wednesday. Okay? Or kind of Wednesday. The state, Alabama Community College System Association, whatever it's called, has its annual meetings Sunday evening, Monday, and Tuesday of Thanksgiving week. So that's always, things are closed then. The meetings this time, I know you're in here, Keegan. You can't hide. There you are. Okay. The meetings this time are down in Mobile, and I wasn't about to drive down there, so most of us aren't. But we do have local professional meetings going on the Birmingham West campus. So that'll be Monday and Tuesday. If you have business with it, even though no classes meet next week, the college is still open Monday, Tuesday, and Wednesday a little bit. Okay? We don't know for sure on that. It will be open on Wednesday, but how long we're not certain of it. Okay? And so if you have business with this college, anytime all day Monday, all day Tuesday. Wednesday, I'd try to get it done. If you have business with the college, right, okay. Try to get it done. Get you on the right line here. There you go. Wednesday morning. Because it's not guaranteed, but quite often on the day before Thanksgiving, they let people go home a little early. Okay, if they do that and you come in Wednesday afternoon, you may find the office closed. Okay, people have already left. So if you do have business with the college, all day Monday, all day Tuesday, shoot for Wednesday morning. We'll probably be open into the afternoon for a while, but I don't know how long. We may be open all afternoon. That may happen too, because it's not guaranteed they'll give us any time off. But if they do, then the offices will be closed at that time. And they never let us know ahead of time. So some years it's been 1, some 2, some maybe earlier, some later, or not at all. So that's going on. Now, so if you need to get in touch with an instructor, though, like I say, we're in professional meetings on the Birmingham West campus. So it's hard to get in touch with us Monday or Tuesday. Wednesday, they usually let us come back to the office. Okay? And I'm planning to do that if they allow that. I think and hope they will. But I don't know which office. I'm hoping it'll be here on Bessemer. But if there's things that have to be done on Birmingham, then I'll be in the office over there. So I suggest if you are going to try to come see me Wednesday, try to do it in the morning and call first, either place. If you don't get an answer, don't leave a message, but call back in a little while. I'll be at one of the two places most of that morning and probably into the afternoon, okay? But I don't know, I won't know until they send the word around, oh, y'all are free to go now. Okay, that's how they do it. Don't know why, but that's how they do it. Okay. After we get back, we'll be back to normal, okay? Whatever that is. Well, for some reason. There it goes. I do know coming up, I think this is during finals week, December 13th. Is that finals week? Anyone happen to know that off the top of your head? Anyone? I think that's finals week. I'm probably not going to be on campus all day that day. My wife's having a procedure. I need to drive her there and drive her back home, so it'll probably take up most of the day. So more than likely, I won't be on campus at all that day. So that's coming up later. We'll deal with that as we get there. All right. Any questions on anything we've covered so far? Okay. We were talking about asymptotes last time. And here's Reggie. Okay. And I never did check. Yeah, I did check. Tell everybody. These. Just one light's on it. Seems right in here. This figure shows the vertical and horizontal asymptotes of graphs of three rational functions. We talked about this one and this one last time. We didn't get to C here. Here is the function. F of x is equal to 2 divided by x minus 1 squared. What's the thing that draws your attention that you have to be concerned with? Anything? X cannot equal 1. Why? That would make your denominator 0. So anything that would make your denominator 0, almost anything, that's going to be a vertical asymptote, meaning the function cannot touch x equal 1, ever, okay? Can't cross it, touch it, or anything else. Okay. And let me get your name, please. Yeah. There we go. Awkward position over here. Okay. So vertical asymptotes, the function can never touch it because x can never equal 1. Okay? Excuse me. Okay. Now, horizontal asymptote. Now, what you could do is multiply this out, but you'll see that's going to have an x squared, and it's going to be the maximum power in the denominator. So look at the ratio of your leading terms, 2 over x squared. What is that going to when x is very, very large? Positive or negative? 2 over x squared. 2 over an incredibly large number. 2 over 10 squared. That's not incredibly large, but check here. It's going to what? Okay. Well, let's see. Above the blue. My pen's not writing well today. Okay. 2 over a large number. 2 over 100. What's that close to? 2 over 1,000. 2 over 1,000,000. What's it close to? Getting closer and closer to? No. The denominator going to infinity, but what's the fraction going to? 0. Absolutely. So therefore, the horizontal asymptote is y is equal to 0. Vertical asymptotes, x equals something, 1. Horizontal asymptotes, y is equal to something, in this case, 0. Now, all three of these had a horizontal asymptote. They don't always. They do not always. Okay? And remember, horizontal asymptote is what's happening in the long run. Very negative or very positive. Can't tell you anything about what's happening in the middle here. Okay? Obviously not 0 here, not 0 here, not 0 here for any stretch of imagination, only in one. So here's the difference with horizontal asymptotes. The function can cross a horizontal asymptote. Now it doesn't cross that one, or this one, but it can. It can touch it. Cannot touch a vertical asymptote, ever. A horizontal asymptote. And here's Skylar. So, any questions on how they look? Now, a couple of these have names. Okay? This one is called a hyperbola. The functions sort of come close together but don't touch. They're two separate pieces. This is a hyperbola. Okay? Come close together but never touch. That may look a little like a parabola. It's not, because of those wings that go out this way. Parabola doesn't do that. But those two, the first A and C, are both what we call hyperbola. Okay. So here's the, whoa. Oh, okay, sorry. They're going to talk about each one of these. I thought I already talked about it, okay? The graphs of f of x equal 1 over x and f of x equal 2x plus 1 over x plus 1 are both hyperbolas. There's the 1 over x we just talked about. The other one is also hyperbola, just what I said. All right, now, here are the general rules. Whew, it's so hot in here. For vertical and horizontal asymptotes of a rational function. Okay, excuse me. Okay. If f is a rational function, and remember what a rational function is? Excuse me. What's a rational function? Okay, a ratio of two polynomial functions. One polynomial divided by the other. We'll call them the n of x, numerator, d of x, denominator, okay? Polynomial functions, okay? Now this polynomial function can be anything here. The a sub n's and n minus 1, all that kind of stuff, are all just coefficients. Those subscripts there, Alexius, right? Okay. The subscripts there are just to identify which coefficient it is. The a sub n is the coefficient. Okay. Pardon me? Oh, I'm sorry. Okay. Okay. The subscripts here just identify the a sub n belongs to the power of x that's n. A sub n minus 1 is the coefficient for the x whose power is n minus 1. That's all these subscripts mean. The superscripts, those are part of the problem. Those are the exponents, okay? And these count all the way down to a sub 1, x to the first, a sub 0, x to the 0, plus x to the 0 is 1. The denominator is a similar polynomial, may have different powers, b sub m, and certainly different exponents, times x to the m, b sub m minus 1 times x to the m minus 1, all the way down to b to 1 times x to the first plus b 0 times x to 0, which is just 1. Now, here's the requirements, excuse me, for everything we're going to do. N of x and d of x can have no common factors. Okay? Z, right? Okay. So, if you have a big old hairy polynomial there, numerator and denominator, first check to see if they are reduced. In other words, you've eliminated any common factors. Because if you have common factors, remember when I hesitated and said the denominator, anywhere it's 0, it's going to have a vertical asymptote? Most of the time, if it's a common factor in the denominator that you can get rid of, then you won't have a vertical asymptote there. What you will have, believe it or not, is a hole in the graph. The graph will still go, but just have a hole there, because you can't have a value there, but it won't be a vertical asymptote. Okay? So that was the only deal there. No common factors. If they have common factors, factor them out. Okay? Now, the graph of f has a vertical asymptote where? Where do the vertical asymptotes occur? Oh, I thought we just said it. Yes, where the denominators are 0. Because you can never divide by 0. So anywhere you have a 0 and a denominator, put your vertical asymptotes right there. Okay? Now, of course, if it was a common factor you got rid of, don't put a vertical asymptote there, but put a hole there. Okay, but you'll get to that later. Okay, the graph of F has one or no horizontal asymptotes determined by comparing the degrees of the numerator with the degree of the denominator. Okay? Now, here's what those rules are. Okay? I've already sort of hinted to them what they are. If the degree of the numerator is less than the degree of the denominator, it's going to have a horizontal asymptote. Okay? And that will be, remember, n is less than m. Okay? So the ratio of this first term, leading term, doesn't matter what the a's and b's are for this one, it'll be, when you do the ratio, if n is less than m, you'll go and wind up with a over b times x to some power. Anytime you have x to some power going to large and large numbers, that value is going to 0. Okay? So when the n is less than m, the numerator's degree is less than the denominator's degree, the graph of F has the line y equals 0, the x-axis as a horizontal asymptote. Okay? Now when n is equal to m, and you do the ratio here, the x's go out, and what are you left with? A sub n over b sub n. That ratio becomes your horizontal asymptote. Y is equal to that. So that would be y is equal to a sub n over b sub m, when n and m are the same value. The ratio of the leading coefficients. Only time that happens is when they have the same degree. Now, if this n is greater than m, it's not going to have a horizontal asymptote. Okay? And the reason is because as x goes to infinity, positive or negative, the ratio here has an x in the numerator, no x in the denominator. That's going to act just like your polynomial, going to an infinity, positive or negative, depending on which way it's going. Okay? So that's the key for the horizontal asymptote. Vertical asymptote, wherever that denominator is 0. Okay. So here's example 2. Okay. Find all the vertical and horizontal asymptotes of the graph of each rational function. Okay? You tell me which way you want to go for first. Vertical or horizontal? I don't care. Vertical. Let's do A first. Any places where you might have a vertical asymptote with that? What do we look for? 0 in the denominator. What would create that? 1 error? Negative 1. 2. 1 at x equal positive 1, because positive 1 squared is 1. Minus 1 is 0. Can't do that. But if x is negative 1, negative 1 squared is still 1, minus 1 is still 0. Okay? An easy way to see that is factor this. And if you factor this, x plus 1 times x minus 1, where is that equal to 0? X equal minus 1, x equal plus 1. Okay? So, those are your vertical asymptotes there. How about horizontal asymptote for A? What would you do? Help somebody. Start the class. What would be your horizontal? It doesn't even have a horizontal asymptote. A. Anybody? Help me. Up here, screen. Any horizontal asymptote? What do you look for? What do you consider? The horizontal asymptote. Ratio of the leading terms. Okay? What's the leading terms here? 2x squared, x squared. So what's the ratio of those two? Forget about that. What's that ratio? A little louder? 2 over 1, or 2. And what do you have out here? f of x, which is, f of x is always, somebody help. Told you that's the one thing you need to remember in this course. Y. Y is equal to 2. There's your horizontal asymptote. Y is equal to 2. Okay? Vertical asymptote, x equal plus or minus 1. Horizontal asymptote, y is equal to 2. How about this one? What might you do to investigate? Factor it. Okay? Later we'll be factoring numerators as well. We're not quite there yet. But now we're just going to factor the denominator. Does that factor? What would it be? Anybody? The denominator factor. Somebody. Okay. X. Okay. It'll be x minus 3 times x plus 2, right? So that x equal 3 and x equal minus 2. And you move them to the other side, right? And you set them equal to 0? Oh, yeah. Yeah, okay. So that'll be x equal 3 or x equal minus 2. Those are your horizontal or vertical asymptotes. I like to say they cannot equal 3 or negative 2, okay? Because you can't, okay? Those are the vertical asymptotes. How about horizontal asymptote? Is there one? Yay or nay? Yep. Is there a vertical asymptote? Horizontal asymptote? It's 1. Okay, ratio of leading terms, x squared over x squared. What's that ratio? 1. And what is it? Y is equal to 1. Vertical asymptote, x can't equal 3 or negative 2. And horizontal asymptote, y is equal to 1. Okay. So, for this rational function, the a one, the degree of the numerator is equal to the degree of the denominator. That means it will have a horizontal asymptote, and it'll be the ratio of the leading coefficients, which is just the ratio of the leading terms, because the x squareds go out. That would be 2, so that would be the line y is equal to 2. Horizontal asymptote. Okay? To find the vertical asymptote, set the denominator equal to 0. Well, I don't like to set it equal to that. I say it can't equal 0. That's just the way I approach it. But they do it this way, which is fine. It comes out being the same thing. And then the good thing to do is to factor. Okay? X plus 1 times x minus 1 cannot equal 0. That means x can't equal minus 1, and x cannot equal positive 1. Okay? Vertical asymptotes. Right there. They say the lines where it's true is where it can't go, which is kind of almost like a double negative or something like that, but whatever. So x cannot equal minus 1 or positive 1, or you just draw those as your vertical asymptotes. Okay? So there's the A. Everybody got it? All right. The equation has 2 real solutions. Oh, they didn't ask for this. Oh, no, that's the denominator. So the graph has lines x, again, I like to say cannot equal negative 1 and cannot equal 1 as your vertical asymptotes. Okay? And they didn't tell us to do this, but this is what this looks like. You don't know what the function looks like until you do another step, and we'll get there in a bit. First, draw in that vertical asymptote. X cannot equal negative 1, x cannot equal positive 1. Draw the horizontal asymptote. Y is equal to 2. Okay, draw that. Okay, now you know the function is going to do something in the middle of those places. Okay, so what you do at this point is test points. Pick something to the left of negative 1, and that would be negative 2. Plug that in your function. They don't, oh, there's the function. So if you plug that in fact, okay. Plug it in here, a negative 2, that would be what? Negative 2 squared is 4, times 2 is 8, and negative 2 squared is 4 minus 1 is 3, so 8/3. Positive. Okay? I know where this function is now. It can't ever cross this line, so it's got to be going up like this, and it will approach this in the long run. So it's going like that. Okay? Now, you're going to have to do 2 test points here, and we'll get to the reason for that later. But in here, between -1 and 1, I would, of course, choose 0, and what does that give you? 0 is 0 over 1, -1. That's going to be 0, okay? Well, that doesn't tell me a lot. It could be going up, or it could be going down, okay? So let's pick another one between -1 and 1. Probably 1/2 would be just about as easy as anything. And here's Ron. So I can mark you from here. I think I can. There you go. Okay. All right. Just realize we're going to have to do another one. So when you do 1/2 here, 1/2 squared is, help me, 1/4. 2 times 1/4 is 1/2. This would be 1/4 minus 1 would be -3/4. So a positive 1, or 1/2 over a negative, that's going to be negative, going downhill. But we still don't know if it's doing like this, so we're going to have to do the negative over here. But guess what? Because that's an even function, it's going to be the same thing on this side that it was on that side. So if you do a -1/2, you're also going to be down here. So sure enough, this is how it looks. It's a 0 here, going downhill both directions. Oh, we didn't do this one. Let's do a 2 over there. But that's an even function, right? So whatever it was here, it's going to be the same over there. So, see, the even and oddness can help you sometimes. It's when it's a neither, you can't say much. Now, they didn't want you drawing it all. They just filled it in to let you see how it fit around the asymptote. But I thought since they did it, I would explain just a little bit of how we do it. We're leaving out 2 fairly important steps here. We'll get to those, I think, coming up right now. Oh, well, here's the B one. They don't list the rational function, but we did it. The leading coefficients of both the numerator and the denominator, well, the leading terms are x squared. The ratio of the leading terms is 1, okay? So the line y is equal to 1 is your horizontal asymptote, okay? Vertical asymptote, finally, they show the function here. What do you consider for vertical asymptotes? Where do you go to focus to see what vertical asymptotes are? Denominator, because you can't have that equal to 0. So we set x squared minus x minus 6, and I'll say you set it so it cannot equal 0. Here's what they suggest. Oh, I blew it. I didn't do what I should have done. We should have factored that maybe. And you see why? We just factored the denominator, and I was going to hold off until later and have you factor the numerator for another purpose. But guess what? Common factors. X plus 2 is a common factor. So when we said x equal -2 will be a vertical asymptote, we were wrong. You have to factor the numerator and denominator. Make sure there's no common factors. So this only has a vertical asymptote at x equals 3. Okay. Now, what's going to happen at x equals -2? I said it earlier, I don't know if you caught it. A hole in the graph there, you're absolutely right. Now, what's going to happen when x equals 1? What will this be when x equals 1? No. What's this going to be when x equals 1? That term, that factor right there. X equals 1, what's this? 0. And guess what? What is this? Y. Y is equal to 0. Okay? That is going to be an x-intercept. Where y is equal to 0, that's the x-intercept. That's the horizontal axis. I'm sorry. Where y is equal to 0, so, and that would be at x equal 1. So 1, 0 will be a horizontal intercept, x-intercept. That would be a 0 for the function. So the function is going through x equal 1. It has a vertical asymptote at x equal 3. Okay? At x equal 2, it's going to have a hole in the graph. Whatever it is there, it's going to have a hole in the graph. Okay? For x is greater than 1, those are going to be positive values, so it's going up toward the, well, we'll see. They're going to draw it for you. Okay? That's a reminder. Always factor numerator and denominator. Don't just factor just the denominator. Might lead you to a bad conclusion. Okay. Oh. What this means, the way they've written it here, when you factor these things out, divide them out, okay, and you write this in factored form as that, in reduced form as that, you still have to say x cannot equal negative 2. Because it can't equal negative 2. But it's not going to be a vertical asymptote. This will produce a vertical asymptote. That produces the whole graph. Okay? We'll see how that happens here. I should have stayed over there probably. Okay? By setting the denominator, x equal 3 of the simplified function equal to 0, x minus 3, you can determine that the graph has a line x equal 3, like saying it that way, as a vertical asymptote. That's true, but I say x cannot equal 3, that indicates it's a vertical asymptote. And they didn't sketch that one. Shame on them, okay? Let's see if they did in the book. No, they didn't in the book either. Okay. They do say it has a hole in the graph there, but rather than take class time to show that, there'll be others, I hope, that will show the holes in the graph. Okay. It's so hot in here. So now we're ready to actually sketch the rational functions. We were sketching them, or at least some of them. Now we're going to give the full range of activities to do. Okay? Now, start over again with what a rational function is. Burning up is what it is. Okay? It's a ratio of a polynomial in the numerator and a polynomial in the denominator. Okay? Now, the denominator is not the 0 polynomial. You just can't have a 0 there. That nothing will work there. But it can be a polynomial. Now, first thing to do, as we just saw, simplify f. In other words, factor everything inside. Factor numerator, factor denominator, see if there are any common factors. If there are, then eliminate it. But don't forget to write on the side x cannot equal those values. That doesn't mean it's a vertical asymptote, but it still means x can't equal those values. Okay. Now, the very easiest thing to plot is the y-intercept. What's true about a y-intercept? Anything? What's true of a y-intercept? Okay, just a few minutes ago we were talking about x-intercept. What's true of an x-intercept? Where y is equal to 0. So guess what a y-intercept is going to be? Where x is equal to 0. So there you go, your two polynomials. Set the x is equal to 0 and just see what the ratio of those constants are, because that's going to be your x-intercept, or your y-intercept. Easiest thing to do, find that y-intercept by evaluating f at 0. That's an easy thing to do. Okay? Now, find the zeros in the numerator if you have it. And how do we do that? How do you find zeros in a polynomial function? Factor! Exactly. Factors at each factor equal to 0. And mark Brian here if he happens to show up. Okay. Good deal. Okay. I've got to find you up here. I think that's you right there. Yeah. Okay? Now, so, factor that numerator, okay? Now, if it has any common factor to the denominator, those have already been eliminated. But you set over to the side and said x can't equal that value, okay? So, the rest of the factors in the numerator, those are your x-intercepts. The zeros of the function are the x-intercept. Plot those. Excuse me. So you plotted the y-intercept, now you plot all the x-intercepts. Okay. So that's how they like to start. Actually, you can do any of these things first. It doesn't matter. Since you factored everything in sight, you factored the denominator too, right? And any place where that has a 0, what does that give you? The denominator is equal to 0. Yeah, it's undefined. What will you have on your graph? A vertical asymptote, okay? So plot those. Those are pretty easy to do too, okay? Now, how about horizontal asymptote? What do we do to determine that? We mark Ashley here. That's all. Okay. Find the ratio of the leading terms. Remember, leading terms, the book loves leading coefficients. There's always a leading term that we really use for the end behavior, okay? Both polynomial functions and rational functions. So we do the horizontal asymptote by determining what the ratio of the leading terms are. If that ratio of the leading term has x in it, not going to have a horizontal asymptote. If it's equal to 1 or equal to a number, that will be the horizontal asymptote. If it's equal to 0, which is also a number, that will be, if the x is in the denominator, that will be y is equal to 0 will be the horizontal asymptote. Okay. Now, once you have, get this, on the x-axis, you have vertical asymptotes and you have zeros. Okay? Now, draw your vertical asymptotes in, your horizontal asymptotes in. Okay? Now, if those points are enough points there, you can tell what's going to go on in that section, you're done. Okay? Just draw it. If you can't, then you do test points. And that's what they say here. Plot at least one point between and one point beyond each x-intercept and vertical asymptote. Okay, now that sounds sort of wacky, but we'll see what happens. Use smooth curves to complete the graph between and beyond the vertical asymptotes. Okay? That's the procedure. Let's put it into practice. It's actually, to me, easier to practice to do than it is to talk about. Okay, the concept of test intervals can be extended to graphing rational functions. Okay, I thought that's what we were just doing. Okay. Oh yeah, we did test intervals on polynomial functions as well. Okay, to do this, use the fact that the rational function can change signs only at its zeros and its undefined values. That's where you would have a vertical asymptote for the x values for which the denominator is 0. Between two consecutive zeros of the numerator and the denominator, a rational function must be either entirely positive or entirely negative if those two zeros fall in between a vertical asymptotes. Okay? If they're on either side, then anything could happen. Okay. So I think it'll make sense. Okay. So let's do something. Oh no, we're still going to talk some more. This means that when put in order, the zeros of the numerator, okay, and the denominator of a rational function divide the real number line into test intervals in which the function has no sign changes. Yeah, that's true. If you include both the zeros and the vertical asymptotes, that's true. Choose a representative x value to determine whether the value of the rational function positive if the graph lies above the x-axis, negative if it lies below, and it's not going to get outside that, in between those, in that test interval. Okay? So here's what, all this is so easy, okay? But let's do it. Example 3. Sketch the graph of g of x is equal to 3 over x minus 2 and state its domain. Okay? Now, just between you, me, and the fence post, I like to always pick out my key things first thing. So what would you like to pick out first? The order doesn't matter. Order doesn't matter. We got 4 things we're going to pick. Yeah, what were you doing? Y-intercept. Okay, that's the easiest one. So let's do y-intercept. Ooh, why is my pen not showing up? Get out of there. Get out of there. Get back. Okay, now. Okay. So y-intercept. Okay, good choice. What is true about the y-intercept? Always. X equals 0. Put x equals 0 in there, what do you get? Second? Okay. In the whole thing. 3 over negative 2, which is? Negative 3 halves. Exactly. So y-intercept is x equals 0, y is equal to negative 3 halves. Always write them as ordered pairs. Okay? And since it's y-intercept, x is always going to be 0. What you want to do next? Anybody? We did y-intercept. We got 3 more things. What are the 3 things? X-intercept. Very good. What's going to be true about x-intercept? Y is equal to 0. What's your y in this case? G of x. Now, can you think of any value of x that's going to make that equal 0? Okay? That'll make the denominator equal 0, which is completely undefined. We're going to get to that in a minute. But in order for g of x to be 0, the numerator's got to be 0, right? Is 3 ever 0? No. So this one has no x-intercept. No way 3 is ever 0, okay? So therefore, it doesn't have an x-intercept, which may lead you to think x equals 0 could be your, y is equal to 0 could be your horizontal asymptote. Let's see. Let's do the test for horizontal asymptote. What is your test for horizontal asymptote? Help me somebody. Ratio of the leading terms. And what's the ratio of your leading terms here? 3 over x. And as x goes very, very large, that's going to, that gets very, very small, going to 0. Okay? Because 3 over x, when x is very, 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 very large, gets closer and closer and closer to 0 in both directions. So, we know that the, goodness rocking around here. Okay, you already said x-intercepts. None. Okay. Now we just did horizontal asymptote. Let me just call that HA. Okay. Okay. The horizontal asymptote is y is equal to 0. That's why there was no horizontal asymptote, because that's your, why there was no horizontal x-intercept, because y is equal to 0 is an asymptote. Never happens here, they never touch it. What's the one thing we're missing? The vertical asymptote. That's going to be your VA, okay? Get out of there, okay. Now, how do we find that? Denominator equals 0, and what would that be? Okay, so here's how I write it. The book doesn't do it. I say x cannot equal 2, because if it did, you can't have it defined. So that's going to give me that. Now we're ready to start the sketching of the graph. Okay, this won't give us the whole graph, but it'll give us the things. So let's first find 0. Okay, let me tick off some points here. Make them angry. Okay. 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 How can I find the point 0, negative 3 halves? Oh, it's there. Okay, good. Where? There, okay, where? Tell me how to find it. You go down 1.5. Right there is your vertical asymptote. I mean your x-intercept. We know there's no, y-intercept. We know there's no x-intercepts at all. None. Zero. Zilch. Okay? But we also know, and let me change color just for a moment here, we know that the horizontal axis, y is equal to 0, is your horizontal asymptote. Okay? So that's why there was no x-intercept. That's an asymptotic line. Excuse me. Okay. Now, what else do we have? And there's the y is equal to 0. So we've done this one. We've done this one and that one. What's the one thing we have yet to do? Vertical asymptote, and that's at x not equal to 2. So I'm going to put the red line here, meaning don't touch it. Don't go there. Okay? Now, the horizontal asymptote, you may touch it. It's still a red line there, but you can touch it. All right. Now, time out here. Before I decide to do any test intervals, I already know one thing of where this function is going to be. Since the y-intercept is here, you know in the long run it approaches the horizontal asymptote, and in the long run, and there's no x-intercepts, so it can't cross the x-axis, but it can approach the x-axis in the long run, where y is equal to 0, that's horizontal asymptote, and since it can't cross the x-axis, it must be heading down here, and it can't ever touch the y-intercept. So we know already, without doing a test interval, we know what the function looks like there. Okay? It's going up here. Oops, let me get my pen back. Okay? So it's approaching the horizontal asymptote there, approaching the vertical asymptote there. Nice, smooth curve. Okay? You already know it. It's part of a hyperbola. Okay. Now, on the other side, this side, we don't know. So here's a good place for a test point. What might you choose as a test point? Anybody? Which do you think? We got everything over here. Pick something on that side of the vertical asymptote. So again? X equal? So again? Someone say something? Excuse me. Excuse me. Okay. Excuse me. Excuse me. Okay. What would be a good test point? Okay. 4 would be okay. 3 would be even easier, right? This would be 3 over 3. It would be 3. Well, there's 3 is positive here. We know where that's going to be too. Because when x equal 3, your y is equal to 3. So it's going to be right up here. And that tells you right now where it goes. It can't cross the x-axis because there's no x-intercepts. So it has, and it can't touch the y-axis. So it has to be going north here and approaching that there. There it is. With only one test interval. Now, they would claim, well, they would say you need one over here too. You don't. You let the y-intercept be your test point there. It's already there. This one you do have to do to make sure it's not down here, that it's up there. And sure enough it is. Okay, that was a fairly easy one to do. Any questions? All right. What I'm going to do is erase my work and let's see how they did it. Okay, they started off just like you did with the y-intercept. You just set x equals 0, and that gives you x equals 0, y is equal to -3/2. Because g of 0 is -3/2. Done. Good choice. Next they did x-intercepts. Okay, that's where y is equal to 0. Y is your g of x, and that's going to be wherever your numerator is equal to 0. And guess what? 3 can't equal 0. So therefore, there are no x-intercepts. None. Okay. Then they go to vertical asymptotes. That's where the denominator is equal to 0. Because it can't be 0. And that would be x equal 2, or x cannot equal 2. That would make the denominator 0. Vertical asymptote. Horizontal asymptote, the ratio of the leading terms. 3 over x, is that it's very, very large, is always going to 0. So therefore, y is equal to 0. And they say because of the degrees. And if you want to remember that rule, that's fine. But if you just look at the ratio of the leading terms, it'll tell you, okay, without having to remember a bunch of rules. Okay. So we've got all that information, and then they do additional points. Something between negative infinity and 2. Unnecessary, okay? But they chose negative 4. Why? I'm not sure, but they did. It's fine. And then they chose 2, something between 2 and infinity. We did choose that. We chose 3, and we got 3. G of 3 is equal to 3, so that's positive. So now we know that the function is there. And you see, it was totally unnecessary to choose this point. They did, it's perfectly fine, but we already had a point there. The y-intercept was there. So we knew that it had to be between those, and then once we found out that was positive, we knew it had to be there. Pretty easy to do. You don't need to fill in every, a bunch of points. You can if you like, but it's not necessary. You know where it has to live. And you know they have to be nice, smooth curves. Any questions? So hot in here. All right. Oh, they did ask that too. What's the domain of that function? You actually could have done that from the very first time they gave you the function. What's the domain of that function? Okay, where do we always assume we're starting? All real numbers, unless something prohibits that. Any prohibitions there? Yes, x cannot equal 2. So it's all real numbers except x equal 2. Now you could write that as from negative infinity to 2 parentheses, comma, from 2 parentheses to positive infinity. You can write it like that too. Let's see how they write it. The domain is all real numbers except x equal 2. Perfectly fine to say it that way. Shorthand, rather than writing out all those words, the set of all x's such that x is not equal to 2. That's the shortest way, most concise way in my mind to write that. Okay? Any questions? All right. Now, shame on them. They did the easy one for you and then left the others undone. So let's go back and do example 4. All right. Hey, yuck, I didn't bring my watch in. Someone will let me know before class is over. Y'all are so kind. Okay. So let's do example 4. Sketch the graph of this one. F of x is equal to 2x minus 1 over x. Okay? And state its domain. I think we can state its domain right now if you wanted to. Can you? Anybody? Say again? X and I equals 0. All real numbers except x equals 0. Yeah, you can just look at that and tell that's going to be its domain. You see why? Because the denominator can't ever be 0. Every other value x will do fine. So we've already done its domain. Domain x cannot equal 0. That's shorthand. Okay. Now, what would be the next things we might want to identify about this function? Guess what? Your domain is almost always also your vertical asymptote. Right? I say almost always because if you did have any of those holes in the graph, x can't be that either. But If you don't have any holes in the graph, no common factors, which this doesn't have, then you can say your vertical asymptote. Since you already have done that, the vertical asymptote is x cannot equal 0. Okay? We've got them both there. Same reason. What you want to do next? I jumped ahead and did that because it was already done. I was lazy. Say again? I can't hear. Horizontal asymptote, since we're doing vertical, we'll do horizontal asymptote. Okay? And what would that be? Get out of there. Okay. Is what? Okay, horizontal asymptote?
She said 1/2.
Okay, yeah, you're absolutely right. Okay. It would be 2. Horizontal asymptote is y is equal to 2. Exactly. Okay? Perfect. Very good. Horizontal asymptote, y is equal to 2. Okay? Remember that when you cover the other terms, it's f of x, which is y is equal to whatever that ratio is, 2. Perfect. What other two things do we want to check out? Y-intercept, and what's that? That's an easy one, right? That's when? That's when? Y-intercept. Where is x equal to 0? And what happens then? We've already said. Twice. X can't equal 0. It can't. Okay? That's your vertical asymptote, so you don't have a y-intercept. So y-intercept is good old none. Okay. One last thing. X-intercept. Okay? And what do we do to get the x-intercept? That's where y is equal to 0. What is your y here? F of x, and how can that ever be 0? Only if the numerator is 0, right? It doesn't matter what the denominator is as long as it's not 0. If that numerator is 0, the whole function is 0, right? Okay? And what will make that numerator 0? 1/2. So x equal 1/2. So, I'm sorry. Yeah, x-intercept would be 1/2, and we said the y was 0. That's it. Okay? Now, we got the 4 things of interest, and the domain basically duplicates almost always the vertical asymptote. So let's start drawing our graph. Okay. Let me tick off a few points. 1, 2, 3, 4, 5, 6. Negative 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Negative 1. Okay. Something like that. What you want to plot first? I don't care, really, much. X-intercept, and that is 1/2 0. Right there. Okay, got it. Y-intercept? There isn't one. Okay, so now we go to our asymptotes. What's our vertical asymptote? X can't be 0, so there it is, the y-axis, okay? And the horizontal asymptote is y is equal to 2. So we go across here like that, if I could line up, but I don't do. Ooh, get out of there, out of there, out of there. Oops, too much. Good, okay. Now, we don't need to do a single thing to the right side here. Why? Because your x-intercept tells you, let me get my pen back, x-intercept tells you it's here, so in the long run this is going to the horizontal asymptote, and as it gets closer to the vertical asymptote, it can never touch it. So, there's that side. Done for you already. You don't need to do a single test point there. How about on the other side? We need a test point. What would you like to use? X equal? Negative 1. Why not? So let's do f of -1. Okay? And what your numerator becomes? 1/2 x. 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 1/2 Help me? Negative 2 minus 1 over negative 1, which would be, say again? 3. Not minus 3, 3. Because the numerator is negative, denominator is negative. That comes out being 3. So at x equals negative 1, your y is equal to 3. Ha! We know where this goes. Has to approach the vertical asymptote that way, horizontal asymptote that way. Nice smooth curve. There we go. Only one test point required. The book might tell you you need one here, one in between these two, or one out there. No, you don't. You know this one's here, so it's got to be there. Once you find this one, it's got to be there. So yes, you only need one test point. Okay? Make sense? All right, that was example 4. How does ours look compared to theirs? Yeah, they did 2 extra test points. I don't know why, but we knew where it was heading. Okay? Yeah. No, it looks like they did 3 extra test points. Knock yourself out. I don't care. Okay. I do. Okay. Sort of. A little bit. Not really. Okay. So, let's do example 5. Red-eyed. Okay. Example 5. Sketch the graph of f of x is equal to x over x squared minus x minus 2. Okay? Now, what would you suggest we do first? And this one, it didn't even say state its domain. We can later if we want to, but what would you suggest we do first? Factor everything in sight. Okay, that numerator can't be factored. How about the denominator? What would the first terms be? X times x. Very good. Then we look where? Sign of the last term is negative. That means these two signs have to be opposite. So one, which order? Negative and positive. Okay, good. And then we look at 2 and say, what's the possible factorizations of 2? 2 and 1. Who's going to win which sign? 2 with the negative sign because it wins, and 1 with the positive sign because it loses the middle sign. Okay? Check it and see, foil it and see. X times x is x squared plus x minus 2x. That would be a minus x minus 2. Perfect. Okay? Now, what does that tell you? All right. Remind me? Huh? Alexis, I thought so. Okay. There you are. Good deal. Okay. So what does factoring that denominator tell you? Anything? Anything? Okay. X equal 2 and x equal minus 1. What are they? Why are you telling me that? Those will be your vertical asymptotes. Okay. So your vertical asymptotes, it doesn't matter what order you do these. Okay. Vertical asymptotes, asymptotes, I don't care what you call them, will be x, I like to say, cannot equal 2, and x cannot equal negative 1. That's how I like to write them, to remind myself, you can't touch it. You can't go there. Okay? There's vertical asymptotes. I didn't ask you where you wanted to start, but we got there, so we did it. Okay? What do you want to do next? I don't care, really, too much. Second? Horizontal asymptote, okay. Since we're doing asymptotes, let's do horizontal asymptote. What tells you that? Oh, get out of there. Is what? Ratio of the leading terms. Okay, I'll come around to do that. I'm going to cover everything that's not a leading term. What's that ratio? Second? 1 over x. Where is that going when x is very, very large, either positive or negative? 0. Okay, so your horizontal asymptote is x as y is equal to 0. Horizontal asymptote, y equals 0. Does everybody see why that's true? Okay. Now here's what you do. Look at the ratio of the leading term. Okay. First, what horizontal asymptote tells you, just like it did with polynomial functions, horizontal asymptote, the end behavior. Okay? Look at the leading things, leading terms. Okay? And with a rational function, you cover everything except the leading terms. That's x over x squared, reduce that as 1 over x. Okay, when x is very large positive or very large negative, 1 over x is getting very, 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 very small. 1 over a million is awfully close to 0. Okay? 1 over negative 1 million is awfully close to 0. Okay? So that's going to 0. So that's what the horizontal asymptote, y is equal to 0. Because in the long run, that's where the function's going. Okay? Does that make some sense? Okay. All right. What's next? We left off the very easiest one. Anybody? What's the easiest? All of them are easy, I agree. Okay. Y-intercept. So what's the y-intercept? What's true about y-intercept? Always. X equals 0. So I'm going to put down a 0 in my ordered pair. We have to figure out what the y value is. Not too hard to do, is it? It's 0 because the numerator is 0. So now we see an example of a place where the horizontal asymptote, you do touch it. Okay? Y is equal to 0. That's 0, 0 is on that line. That's fine. You can touch a horizontal asymptote. You can't touch a vertical asymptote. All right, now we need, and by the way, how many y-intercepts could we possibly have? Why? Y-axis is a vertical line, and the vertical line test says only touch a vertical line once. May not touch it at all, but it sure can't touch it twice. If it did, it wouldn't be a function. Okay, so if this is a function, which it is, it can only touch it once. So only one y-intercept. Okay, how about, or you may have none. How about x-intercepts? What do you do there? Not that hard. Set y equals 0. So y equals 0. And how can this thing ever be 0? Only if the numerator is 0. Hey, guess what? 0, 0 is also the x-intercept. So nothing new there, folks. X-intercept is also 0, 0. Now, you can have more than one, but if that's a linear numerator, you only have one. If it's a quadratic, you may have 2. A cubic, you could have 3. You know how it goes with those numerator polynomial. That's all the information we're going to get out of this, and frankly, it's paltry. We're going to have to do some test points on this one. But let's plot what we know. We'll tick off some points here. Okay. Now, what things can we put in place?
0, 0.
Say again? What did you say? Someone said something. 0, 0. Okay. Big, tough one. Okay, 0, 0. I can even plot that. Okay. That's your x-intercept. That's y-intercept. Okay. We got those two done. Vertical asymptote. So I'm going to go to my red pen to do that. And what are those again? Okay. Y or x cannot equal -1, so that's going up and down there. And get out of there. +2. Another vertical asymptote. Okay. Now one more. Horizontal asymptote is y is equal to 0. Okay, there it is. Get out of there. Okay. Hey. We need some help here with test points. Why? We have no clue of what's going on this way. So we're going to have to pick one test point to the left of your first vertical asymptote, we're going to need another test point in between vertical asymptote and your 0, because you don't know whether it's going up or down there. So we need another test point in here, you need another test point over here, and we need a test point out there. 1, 2, 3, 4 test points. Gotta have them. So you get to choose what you want to use for your test points. Yes? Why did I do that? Because we determined that the horizontal asymptote was y is equal to 0. Now how did we get that? We looked at the ratio of the leading terms. X over x squared. That's 1 over x. And as x is very, very large, positive or negative, that's what horizontal asymptote tells you. What's the end behavior? When x's are very large. 1 over x is going to be going to 0. Right? Oh, the y-axis. What about it? No, it's not. The only two vertical asymptotes are x not equal to 2 and x not equal to negative 1. The y-axis is not a vertical asymptote because we already saw it. You can have x equals 0 there. 0, 0. That point is on it, so it can't be a vertical asymptote. Right? Okay. Got it? Okay. All right. So you need to choose me a test point for x to the left of your first vertical asymptote. That's x equal negative 1. Something to the left of that. Negative 2. So let's do, see what color am I now? I may not have heard well, but it doesn't matter. Okay. Okay. F of negative 2. So let's just plug a negative 2 in there. And actually, I like the factored form better. So the numerator will be negative 2. The denominator will be, what's minus 2 minus 2? Negative 4. And what's negative 2 plus 1? Negative 1. Right? So what does that give us? Negative 1/2. So it's down here, just about there. That's all we need to know, folks. Because from here, it has to approach the horizontal asymptote, and from here, it approaches the vertical asymptote. That's all we need. Okay? How about between negative 1 and 0? Is it time? It is? Or is it close?
No, it's like,
Huh?
9:47.
Oh, past time. Oh, how could it be? Y'all can finish this one at home, can't you? Okay. We'll start next time with... Wait, before you go. We'll start next time with example 6. That will be the most fun of any of these, even though they're all fun. But also, you can do some homework exercises. You can do either 5 or 7. They're both at calccheck.com. 7's at CalcView. You can do any of the odds, 9 through 15. They're all at CalcChat. 15's at CalcView. I think you can do all of 17 through... You can try it, 17 to 37. They're at CalcChat. 27's at CalcView. And we'll stop there. Because I knew you wanted something to do over this week of holidays besides eating turkey. Okay? So now you've got some free calculus to do. Thank you. All right. Good deal. All right. Take care.
I don't know about the grade.
What's that? Yeah. I'm sorry. Thank you so much.
I'll be.
Okay. Good deal. Thank you.
All right. We'll see.
Thank you.
I didn't say that.
That's all right. I'll keep them together. I'll try anyway. Okay. Oh my goodness, I'm so hot in here.
Yeah, it is so good.
What's that?
It got hot in here.
Yeah. All these hot bodies.